27.020, okay, or 27 times 10 to the power 6 Pascal. Okay. So now we are going to draw an element. Okay, we are going to draw an element. Okay, so we know our value. So on the left hand side is consider the shear stress is due to torque in the x direction only. Okay, so we have found that it's in tension, right? So this is equal to 27 times 10 to the power 6 Pascal, and we have a shear of due to the torque only is 21.618. Okay, 21.618 times 10 to the power 6 Pascal. Okay. On the right, we are going to consider the shear stress is due to Tx and Bz, right? So now we have 27 times 10 to the power 6 over here, Pascal. Now the torque is equal to 21.618 times 10 to the power 6 plus by 1.561. Okay, 1.561 times 10 to the power 6. Okay, so 21.618 power 6 plus 1.561 power 6 is equal to 23.179 times 10 to the power 6 Pascal. Right. So from here, right, we know that the stress average is equal to 27 times 10 to the power 6 divided by 2, right, which is the center of the circle. So 26 power 6 divided by 2 is good. 13.5 times 10 to the power 6 Pascal. It's the same, okay, because the normal stresses are the same. This is also equal to 13.5 times 10 to the power 6 Pascal. Okay. Then the tau max, the maximum shear stress, will be equal to 13.5 times 10 to the power 6 squared, okay, plus by 21.618 times 10 to the power 6 squared. Okay, so this is equal to 13.5 power 6 squared plus by 21.618 power 6 squared. Square root of the whole thing is 25.487. 25.487 times 10 to the power 6. Okay. And the tau max is equal to 13.5 times 10 to the power 6 squared plus by 23.179 times 10 to the power 6 squared. Okay. So the shear stress over here, maximum shear stress is 13.5 power 6 squared plus by 23.179 power 6 squared. Square root of the whole thing is 26.824. Okay, 26.824. Okay, 26.824 times 10 to the power 6 Pascal. Okay, so now when we calculate stress max, it's equal to 13.5 times 10 to the power 6 plus by 25.487 times 10 to the power 6. Okay, so 13.5 power 6 plus by 25.487 power 6 is 38.987. Okay, 38.987 times 10 to the power 6 Pascal. If we consider the shear induced by the shear force, plus by 26.824 times 10 to the power 6. Okay, so 13.5 plus by 26.824 is equal to 40.324. So we can see there is some difference. Okay, so the difference is equal to 40.324 times 10 to the power 6 minus by 38.987 times 10 to the power 6. Why I do that, I use the one without the shear stress, without the shear force as the reference, because the formula that we derive to get the diameter, which is this formula over here, right? This formula over here, ignore the shear force. So this is our benchmark, okay? So this will come out, the difference is equal to 40.324 minus 38.987 is equal to 1.337 times 10 to the power 6 Pascal. Okay. And if you calculate the difference in percentage, so this is 1.337 times 10 to the power 6 divided by 38.987 multiplied by 100. Okay, so 1.337 divided by 38.987. The difference is only 3.43%. Okay, is very small, right? So that is why we can ignore. Okay, so therefore we can the shear force can be ignored during shaft design. Okay. So if at any chance that you are asked to prove why you can ignore, this is what you have to do. That you have to show with and without, and you calculate the principal stress. Okay. And you realize that we did not get, remember, our size is controlled due to 50 megapascal. Yes or no? Right? Our shear stress allowable is 50, right? So you realize that our stress max, right, is 40.324, not really at 50, are we? And the reason is because, right, we have selected based on the 323 and not the 116.06. Why is that? Because we want to see the effect of with and without the shear, with and without the shear force. Okay, right. So that's all I have for today. Okay, and what I'm going to do is I will post this, and I'll still stay behind if you have question. If not, thank you for your time. And it's really warm, and I regretted not turning on my aircon. Okay, and I'll see you guys on Thursday.